Hello, in this video, we'll go over an example of using Tensorflow to custom layer and gradient tape to implement a variational autoencoder. So first import the libraries, and then once we import the libraries, we'll set the parameters. So again, it's a similar structure, 128, 258, 784 of like the autoencoder example in the previous lecture. We'll just do a similar thing, but using the variational autoencoder. So load the data like as a NumPy array, and then we need to convert it to the data set using the from tensor slices here. So this will get us the TensorFlow data set format. So here's the VAE class. And it has the hidden dimension and the latent dimension. So we declare all the custom layers for 1, 2, 3, 4, 5. So that's what we use. So let's see how we use them. So the encoder will have the value of the layer 1. So here, get out the hidden dimension. And then from that, we'll get the layer 2. So take the H, so it gets here. And then FC3 here gets here. All right. So these are 2. Why do we get 2? Because one we want for the mean and one for the variance of the log variance of to create the sampling, isn't it? So we get 2 out. And then the reparameterizing function is that it takes the mu and log variance and pull out a random sample from there, isn't it? So this is sort of the reparameterization trick that we usually know from the mean plus some random normal times the standard deviation. And then the decoder is that you get the latent dimension and then transform it to FC4 here, to size of the hidden dimension, a hidden layer dimension. So get the H. Of the H, you get out the replicated image F5, isn't it? And the decode is that if you transform it to the sigmoid, so that was just getting that out as a linear function, and then transforming to the logit. Okay. So, and then the call is actually how do we do this in the forward pass? Well, you get the input, goes to the encoder to get the mu and log variance, reparameterize to get the latent data pointer Z, and get the Z, you get the reconstructed logit. So you this VAE structure call gets the reconstructed logit, mu and log variance. Okay, good. So that. Let's build a model and call it model. We use Adam Optimizer. And then here's the training. So we'll say the batches of for each epoch, enumerate training data set. So remember, this is a TensorFlow data set. So you can just call one, and then you get all this data here. So the X is actually what we want. I'll get the 784 pixels of X. And then what do we compute the gradient of? Well, first we get the model of X, get this reconstructed image. And from that, we will compute the reconstruction loss. And then one more special loss for the VAE, isn't it? The KL divergence, which we compute here. The KL divergence and the reconstruction loss together will be our total loss. That is what we want to compute the gradient of, which here the gradient tape gradient of all the trainable variables updated such that to minimize the losses is what we do, isn't it? And then the gradients, we clip it just to make it reasonably stable. And then here we update actually the nodes based on the gradients computed here. Okay? So this we train and we show some intermediate step. So this is going to take a while. So let's come back when it's done training. Okay, now it's done training. So let's see the original and the reconstructed images. So we'll again look at the X-test and the reconstructed test and take 10 of them to show. And here you can see that it sort of does it. The background's a little bit blurred, but still you can see that it did create it, the images. Okay. But this is how one can implement using the gradient tape and custom layers to implement the VAE. Thank you for watching this video.